morning or good afternoon, depending on where you are. I'd like to thank you for joining us today for our 176th webinar in our monthly webinar series. Today's featured presentation is a one-sided approach, the longitudinal launch of the Pretty Rocks slide. This is about the launch of a 425-foot Warren Truss in Denali National Park. It's a fascinating project. Justin Sieg and Chris Sweetgall with KWH Constructors will give us all the details. They are joined by Devin Altman from Jacobs, who will be introducing the project. We'll start with a few announcements and then move into the presentation that will last approximately 40 minutes. The presentation will be followed by a question and answer session. My name is Kathy Kroll. I'm a co-director of technology transfer for the IBT ABC UTCs at Florida International University. I'd like to start by thanking the United States Department of Transportation and its University Transportation Program sponsors the IBT ABC UTC. The University Transportation Centers program has been in existence since 1987 with the mandate to help address our nation's ever-growing need to maintain and enhance our transportation systems. The IBT ABC UTC at Florida International University and our partner universities are focused on accelerated bridge construction and innovative bridge technologies. We would like to express our appreciation to the US DOT and their UTC program for supporting the IBT ABC UTC so we can continue to serve the bridge engineering community with events like this webinar series. Before we get started with today's webinar, I'd like to share a few announcements. First, the 2026 World Bridge Engineering Conference that is coordinated by the IBT ABC UTC will be held in Miami, Florida, December 1st and 2nd of 2026. This conference is co-sponsored by the US DOT and over 32 state DOTs. We're currently accepting abstract submissions. The deadline is March 20th of 2026. For additional information of all things related to the conference, please visit our website and/or use the QR codes on the screen. In addition to abstract submissions, we're also accepting award nomination submissions for Innovative Bridge Engineer of the Year, Innovative Bridge Agency of the Year, and project awards for both ABC and IBT in the categories on the screen. Again, see our website and/or use the QR code on the screen for additional information and submissions. On to our industry event. The first event of 2026 is the Transportation Research Board's 2026 annual meeting in Washington, D.C. from January 11th through the 15th. Registration is open. Next is the 2026 PCI convention at the Precast Show. It will be held February 2nd through the 6th in Kansas City, Missouri. Registration is open. The AISC NSBA's 2026 Steel Conference will be held April 22nd through the 24th in Atlanta, Georgia. Registration opens in January. For industry news this month, we recently held our annual advisory committee meeting for the UTC. Since the information is fresh, I thought I'd share some information with you on this webinar series. I'm showing data on one representative webinar, but the statistics are fairly consistent across the webinars. As you can see, we have an international audience. Our friends in Canada are consistently our highest attending country. It's interesting to note that we typically have in the range of 10% international participation. Within the US, it's interesting to see participation on a state-by-state basis. I included a blow-up of the top participating states since it's tough to see the very small font. Sorry about that. Pennsylvania is almost always our leading participant. So a shout out to Pennsylvania for your state's interest and support. The last slide on this topic is a breakdown of affiliation. We are consistently in the range of 20% governmental attendees, which includes both state and federal, with 60% from the consulting community, with the balance made up of various other affiliations. The UTC always finds those statistics interesting. So our next monthly webinar will be on Thursday, December 18th from 1 to 2:15 Eastern. The presentation will be the next generation of pre-stressed, precast, concrete, deck beam bridges. Mike Como will be presenting. As many of you know, Mike is a frequent contributor to our webinar series. He's an engaging presenter and always includes valuable details and resources. Please join us next month. Registration is open. That's all for our announcements. On to our standing housekeeper items. As many of you may know, these webinars are recorded and posted on the IBT ABC UTC website in the section titled Monthly Webinar Archives. so you can access this and all previous webinars for future learning and to share with interested colleagues. I'd also like to point out that the PDF version of today's presentation is provided in the GoTo dashboard on the right side of your screen. You can download these PDFs during the training session. They will also be posted in the archives. I re-emphasize this resource. We sometimes have latency issues where the audio and video are not well aligned. If this is your experience, we encourage you to download the presentation and follow along in real time. We're working on improving this issue. Lastly, this presentation will be followed by approximately 15 minutes of question and answer. We have a number of questions that are submitted with registration. With that, we begin our featured presentation. We are happy to welcome Justin Sieg and Chris Sweetgall from KWH Constructors and Devin Altman from Jacobs. Thank you all for sharing your time and expertise with us today. With that, we'll turn the screen controls over to the presenters.
All right, thank you, Kathy. I'm going to go ahead and start with the introduction. And what you're seeing right now on the title screen, the far left photo shows the completed permanent bridge in the Valance cantilever state. Notice the large 130 kip crane at the end of the cantilever and the scissor lift. We also built a bridge within a bridge for this project, so you can see the launching nose nested inside the permanent structure. And on the bottom right, you'll see the launching nose extended across the landslide, resting on the receiving tower prior to the combined truss launch. For this project, we are in Alaska, the largest state in the United States, and we are in the third largest national park in the United States of Denali National Park, kind of in the south central portion of the state. This is one of the main reasons folks come from near and far to visit the national park. It's the beautiful scenery. It's the tallest mountain in North America. Some beautiful natural wonders. I encourage everyone to join us at the park at some point if you've never been, or if it's been a few years since you've been there. Along with some of the beautiful wildlife we have are grizzly bears, caribou, wolverines, tall sheep, beautiful species of birds and moose. These bears were even in camp. Here we are a little more zoomed in on the project, and you can see the escarpment here where this triangular region is where the Pretty Rocks landslide is, and the Pretty Rocks region gets its name from the Pretty Rocks in the polychrome region. And over here on the right is a national park map, and you can see in black the area we have access to, and red is where we currently do not have access to. The Denali Park Road is the only road in the park, so it is where a lot of the adventures begin and hikes and expeditions go from. So it's a big need to bring it back into access and accessibility to the western part of the park. So as I mentioned, half that park is closed due to the landslide taking out the road, and that has led to the consequence of more than $1 billion per year in revenue from the Alaska local economy. That is a trickle-down economics where more than 600,000 tourists each year come to the park from all over the world. The mountain is often only visible from the end of the park road, so this is another need to get it back up and running so people can get there. Showing a little bit of the history of the slide movement over the year, we have ice-rich soils here with permafrost that some of the increased temperatures have been melting and leading to some instabilities for the landslide movement to progress. Starting in the early 1980s, it was only needed a little bit of maintenance here and there every couple of years. By the end of the 1980s, we then progressed into needing annual maintenance to service the road. And then in the early 2000s, we're talking about inches per month. And as we progress towards the end of the 2010s, we get to feet per month, and finally 5 feet per month when the Park Road was closed and no longer allowed to be serviced at the end of 2021 season. This is a project timeline, really shows from when the contract was awarded. BGC Engineering and Jacobs began to work on design at the end of 2019 and the beginning of 2020 on some of the type, size, and location selections for the project. But you can see we really began a lot of the work progressing preliminary design to final design in early 2023. The first construction season was that summer. It is a very shortened construction season with only really 5 months we can count on for construction season. So there are 4 seasons planned of work, 3 have been completed, and we'll go into more detail, but the project is scheduled to be completed here at the end of this summer in 2026. So due to the site constraints and trying to span the landslide, what we ended up with was a 475 feet steel Warren truss. It helped fit the site really well to span the gap and go over the landslide. It also helped that the park road itself is quite narrow, and we only have an 18-foot wide roadway. And so with the 475 feet, we have about 10 panels, with each one being about 47.5 feet long, and that led to easily shippable pieces, nothing longer than 50 feet, so that everything can get to the remote site easily and readily. We ended up with a Warren truss after looking at a couple different options, but because we have a lot of different configurations and stress reversals, different diagonals will be going into tension or compression, it set up nicely, and it gave us the right combination of stiffness that we were looking for. The other thing we're not really going to talk as much about today, but I did want to mention, is the geotechnical components and the soil structure interaction that we have. And we wouldn't be able to be possible to be talking to you today about the erection methodology without. So we have, I think, almost 3 miles of steel for substructure foundations for the permanent structure. And those include ground anchors and micropiles, rock dowels on the west side. We also have a soil nail wall on the east side and other soil anchors and micropiles as well. So we wanted to keep things rather simple. So all of the cord members are box shapes, and the end posts as well. All the diagonals, except for the end posts, are H shapes. We have this most complicated shape probably is this 5-sided top portal strut. And we also had built up I sections for the floor beams and rolled flange beams for the stringers and top and bottom lateral bracing. We also have a lightweight sandwich plate system, SPS deck system, which has 2 thin plies of steel and a polyurethane core that helped us save on weight for the structure. And one of the other unique aspects to the construction is the fasteners being used. These are new in the AASHTO LRFD Bridge Design Specifications 10th edition, and they weren't in AASHTO at the time we designed them, but is the TNA torque and angle Group 144 fasteners. So they're able to be tightened from just one side. This spline is fixed and doesn't come off like a TC twist off bolt. And this gun down here has a dual socket. The inner socket grabs the spline, the outer socket grabs the nut, and is able to tighten the bolt from one side once again. And all of the fasteners were exterior facing for constructability. I mentioned some of the geometry already. The out-to-out width is about almost 26 feet. The client for this project is Western Federal Lands, the Highway Division of FHWA. The owner of the bridge is the National Park Service. Prime consultant was Jacobs, and BGC Engineering was the geotechnical subconsultant for the project. And over here you can see a typical section. You can see the floor beam, the stringers, the SPS deck, along with the guardrails on the outside and the narrow roadway width, which I'll point out, if anyone has an 18-foot roadway in the future, the MBE manual makes you load rate for 2 lanes, and you only design for the bridge design specifications for 1 lane. And for this CMGC delivery method, I really want to commend our dream client, the U.S. Department of Transportation, for fostering innovation and collaboration very early on in 2023 that allowed KWH and Jacobs and Granite and FHWA, everybody to work together very early in the process to design for constructability and erection means and methods to get going on a BIM for bridges model and get the lead time going for steel to get the need back of reestablishing the road as soon as possible. And with that, I'll go ahead and pass it over to Justin.
All right, thanks, Devin. As Devin said, the MGC process was utilized, and we were able to be brought on board early, KWH constructors along with Somerset Engineering, during the pre-construction phase. The first task we had was to select the bridge erection system. It needed to be selected first because this complex erection, it would control the final design of the permanent structure as well. At RFP time, there was a 2-sided progressive cantilever approach with highline to transport the material across the slide. And then post-award, 2 other options were considered: a 1-sided temporary cable stay and a launch truss launch methodology. The RFP concept, progressive cantilever from each side, utilizing a highline, had some challenges. There was a lack of geotechnical information at highline stay locations, stay foundation locations. When we did receive additional geotechnical information, the data showed unfavorable conditions behind the west abutment, which would be over here. That further geotechnical information showed ice-rich collidium behind that abutment, which was unsuitable. There was an issue with the feasibility of the wind guys due to the magnitude of the wind in securing them. And it was difficult to mobilize a large enough crane to erect the highline towers, which would be approximately 160. The second concept of the one-sided temporary cable stay approach was good in that we're directly erecting the bridge like the previous, and it did not rely on temporary foundations on the west side. It still had the issue of the feasibility of wind guys due to the magnitude of the wind, and the duration of exposure of the wind was high throughout the erection process. The exposure or the area of the structure got worse and the magnitudes of the loads got worse. And there's unpredictable wind conditions at this site. The last considered was the bridge erection system of the launch truss launch. This did not rely on temporary foundations on the west side either. It was had the best ability to resist wind loads due to the bridge being erected at the central line of abutment 1 and utilizing 3 bays of the bridge to resist that wind load. We could build the entire truss and build the launch truss inside the truss and choose when to perform that launch truss launch and each of the combined truss launch activities, where we had stopping points where we could wait for a weather window. Ultimately, the launch truss launch methodology was selected as the wind exposure periods were less, and it didn't rely on temporary foundations on the west side or access across the unpredictable landslide. When the bridge erection system was selected, the next step was to progress to the design of the permanent structure and the bridge erection system. The CMGC contracting method allowed for constructability during the design phase of the permanent structure because of the ability to perform a parallel design of the bridge erection system and the permanent bridge. The erection engineer was able to work closely with the bridge engineer to consider all load cases during construction, many of which are controlling loads due to the complex erection method required. We knew the permanent structure would withstand the forces imposed during erection because of this intimate coordination between the erection engineer and the design engineer. Once we were able to develop those loads and start to have confidence in the member sections of the permanent bridge, we introduced the IDD, or Integrated Design and Detailing process for the main bridge. We were able to work collaboratively and implement this process. We brought on DBM Virkon as the detailer to begin building a model that would ultimately be used for fabricating the permanent bridge. That's a large difference and is not done very often at this stage, but we were actually creating the model with enough accuracy to fabricate the bridge from. We started the process by creating a 3D wireframe to agree on the geometry. We then infilled main member cross sections. Once that was decided by the design team, we were then able to produce an advanced bill of materials, or ABM, for solicitation of the main member plate. We were able to award the mill order to a fabricator, and that duration of the mill order, which was approximately 6 months, was able to happen at the same time that we were completing the connection design and the final design of the bridge. It also allows for accelerated connection design. So I'll show you each of these steps. So the 3D wireframe is what I'm showing here. This is the first step, create a general geometry and also camber. So we were able to have this model approved as the basis. We then worked into the main member model. We use that terminology because it's more than what you would call the primary members, but we focused on all the members that required welding in the fabrication process. These are all built up sections, as Devin said. They were designed as node to node. The data that we can export from the model is shown up here. Once we had that solidified and approved, we were able to produce this advanced bill of materials and make it easy to get accurate pricing from a fabricator and then move into the award and procurement of this material. I just wanted to note that some people may think it's odd to have the fabricator on at this time. This was a fast track project with a goal to open the park road as soon as possible. It's interesting that the fabricator that procured the primary plate did not end up being the fabricator that fabricated the bridge. So you're not necessarily stuck at this phase with an initial fabricator. Now that the mill order was placed, we could focus on the connection design. This is a view of a Trimble Connect module. The bridge was modeled in Tekla, and we used Trimble Connect as the medium to view and review and approve things. So this is a to-do module. The detailer would receive connection information that it was tabular and schematic from Jacobs, and we would detail that in the model. On the right side was what was on that information, and on the left side was the proposed always, and we would work through this efficiently. It was very streamlined, and we had direct communication between the detailer and the design engineer. This is the final outcome, the model, showing the most complicated connections, and as you can see, it was beneficial for everybody involved to this detail of a model at this phase of the job to ensure that everything that we were designing worked. Another benefit of the CMGC process was the ability to have the temporary foundations designer on board during the pre-construction phase. This is a very unique geological site and varies wildly. We had very little geotechnical information in the area that we needed temporary foundations. We completed the preliminary design during pre-construction. We were then able to perform a test pile program at the end of the first season, as you saw in the schedule, to confirm that design. And over the winter, we were able to finalize the design and ensure that we gave the construction team a design with confidence and that we wouldn't see unforeseen conditions. So it was a real risk mitigation strategy, and we were able to have a lot of confidence in installing this temporary foundation system in the production pile phase in season 2. These are all examples of benefits of the CMGC process, but it's not meant to be all-encompassing list, as there are many more benefits of the CMGC process. These were just focused on the design phase of the project. Now that we have the background of the project and have gone through the design phase of the permanent bridge, Chris will begin to look at the installation sequence and the details of the design of the bridge erection system.
Thanks, Justin. So the first step in the installation process was to install the foundations in the launch bed, as Justin described, and then to assemble the main truss on top of them. The first 4 bays of the truss were erected using a land-based crawler crane left over winter between the first and second construction seasons. At the start of the second season, a small telescopic crawler crane was placed inside the truss and was used to erect the remainder of the truss in a balanced cantilever progression, as seen here. The next step was to construct the launch truss within the main truss. The launch truss was progressively assembled on rollers 1 bay at a time, and each bay was shuttled forward until the truss was fully installed within the main truss. The launch truss was then launched to the receiving tower. Using the jacks on the receiving tower, the tip of the launch truss was raised about 7 feet to counteract rotation and deflection so that there was a level support for the combined launch. The combined truss was then pulled across the slide using strand jacks located on the receiving tower. Once the combined truss was across the slide, the jacks in the receiving tower were used to lower the west end of the bridge to its final elevation. Next, on the east end of the bridge, a jacking frame was constructed within the launch bed and used to lower that end to its final elevation. The final step was installing the SPS decking plates and bolting them to the stringers. So a quick recap of the launch system components. We have the launch bed, the main truss, the launch truss, and the receiving tower. The launch bed was used to support the main truss during erection, including over the winter, and then again during the cantilever phase of the launch truss launch. It then provided a launch track for the combined truss during the combined launch. And it was built out of W36 by 529 launch beams, as well as C15 channel tie downs and HP16 by 121 outriggers to support the truss under winter loading conditions. The receiving tower was intended to provide a variable elevation support for the launch truss and the combined truss. And it consisted of HP 18 by 204 columns reinforced with double C15 by 50 channels. And these were the largest sections available to us at the time. They're due to time constraints, there wasn't time to fabricate a custom section. We had to get the pieces across the slide before access was lost. At the top, we had 400-ton center hole jacks with 3-inch diameter bar, which was the largest high-strength bar commercially available. And we had double 200-ton rollers just to support the launch nose and 70-ton strand jacks to pull the combined truss across. The main truss was designed by Jacobs Engineering, and it was 475 feet long, but by about 25 feet wide and 50 feet tall, 24 feet wide. Weighed 1.6 million pounds, and it was split into 10 bays. It consisted of built-up box and H sections, rolled W shapes, and built-up crowned floor beam. There were 24,000 1-inch diameter TNA bolts in the structure. And in this photo, it's shown fully assembled by KWH at the fabricator's facility, Gunderson Marine in Portland. This was a necessary step taken by KWH to ensure proper fit up of the job site. The launch truss had to span the 237-foot gap between the main truss and the receiving tower, and it was 392 feet long, 20 feet wide, 25 feet tall, and weighed about 636,000 pounds. We used almost all types of steel generally available to construct the launch truss. There was 100 KSI connection plate, 70 KSI plate, 50 KSI plate, plus rolled channels, I-beams, and angles. And it used 9.3 thousand 1-inch diameter bolts. And now Justin's going to talk through the interfaces between the various launch system components.
The first interface to look at is between the launch bed and the main truss. The main truss needs to be statically supported during main truss erection and the launch of the launch truss. But during the combined truss launch, needs to allow movement. Support over abutment 1 had to resist a very high load due to extreme cantilever during the launch. It was not economic to have a support capable of moving at this point due to the high load and it being at the end of the launch beam. Simple system was developed that can be shown, that's actually shown here. Photo, it needed to allow some rotation due to the cantilever and the deflection associated with that. To accommodate that, we simply used a cotton duct pad, or more commonly known as fabrica. At all the other remaining support points, we were able to incorporate the roller necessary for the launch into the static support, so that the supports didn't need to be changed out prior to the launch. Looking over here, you can see a typical roller section. This is beyond the launch beam. We had 500 ton to 300 ton Hillman rollers that were fastened to a single rocker frame and then connected to the structure. We had on the edges Hillman's AccuRoll guide system. These were semi-custom rollers in the capacity that we had, we made them narrower and longer to better suited for the launch and loading directly over the web of the beams. You can also see our tie-down system here over the portions in land that were in use during periods of the West Progressive Cantilever and the launch truss launching operation. And over here is a photo of one of the rollers on the launch beam at the start of the launch. To the left, you can see the wind restraints that Chris was mentioning. The next interface item is between the main truss and the launch truss. This is depicting the equipment used at the western end of the main truss, or at L0. There's lateral guide rollers off to the side that follow the top and bottom flanges of the bottom chord of the launch truss. And you can see custom grooves are present in the chain. That's those black lines to prevent chain sag for their use in the vertical application. Then we have the vertical support rollers on custom single rocker frames to enable direct attachment to the permanent stringers here and here. And this is what it looked like once the launch truss was launched and we were installing the connection between the main truss and the launch truss prior to the combined truss launch. Interface item to look at is between the main truss and the launch truss is at L3. We have some very custom uplift rollers here. They're actually combination vertical support rollers and uplift rollers. The bottom portion needs to supply vertical support during some phases of the launch truss launch, and then these upper cams prevent rotation of the launch truss during the latter stages of the launch truss launch. We have stringer tie downs at the bottom, react at upward force, and then we have the same lateral guide rollers. We have this temporary tow bar, a winching beam, and then we have a longitudinal stopper once the launch truss is fully launched to fix it in that location. Let's look at what this looks like installed in the field. Yes, so you can see the longitudinal stopper and that custom vertical support / uplift roller here. You get a better look at it here with the launch truss installed. And then this was prior to the launch truss getting to its location. So you can see inside the chain roller for vertical support and the lateral guide rollers. Now that we know the interface items, we can look at the movement systems. We utilized 2 hydraulic winches to launch the launch truss. One was the primary winch to advance the launch truss to the west, which is shown in red. The other was a tailhold winch shown in blue, which provided protection if the bridge were to overhaul due to unforeseen tailwind. So the reading went from the winch, it went down the stringer all the way to the winching post. That was located at L2, which is 47 feet 6 inches past the stopping point at L3. Went back, connected to that winching beam that I showed at the end of the launch truss, went through here, all the way back to the winching post, down, and all the way back to the structure. This is what it looks like installed. This was the hydraulic winch, which gave us a lot of control during the launch. Went out of here, down to the winching post, back up into the winching beam, over, and then dead ending back at the frame. The last mechanism for movement was for the combined truss launch. We mounted strand jacks provided by Enerpac to the west face of the receiving tower columns. We ran strand from there to the L0 node of the permanent structure. This method was selected because it provided controlled movements and directed the bridge to where it was supposed to go, lessening the guiding forces required. So the whole system is shown here with strand jacks, strand running across, and the anchorage. And this is a close-up of the strand jack and a close-up of the anchorage with the L0 node. Now that we understand the system interfaces and the movement mechanisms, Chris will talk about the details of the design of the bridge erection system.
Thanks, Justin. So this being an FHWA bridge project, we used AASHTO codes for the design. The main reference used was the LRFD 9th edition, which was in effect at the start of the project. The 10th edition was released toward the end of the design phase, and there were certain specific refinements that were used in our design in a limited capacity. Since the bridge erection system was mostly temporary components, the guide design specs for bridge temp works were applicable, and it was also necessary for us to reference ASCE 7 for load development. And I'll go briefly through some of the loads that were taken into account in the design. So dead load controlled in many stages, especially for low wind stages, and we used a load factor of 1.4 throughout, which is arguably conservative given the level of certainty of the member self-weights. Wind loads, we based our wind loads on a climatology study and wind tunnel testing done by RWDI. You can see here their scale model that they put in their wind tunnel. We monitored, wind was key for many of the launch stages, so we monitored wind speeds throughout construction using weather stations that had satellite uplinks. And we planned our launch operations based on customized local forecasting given to us by our WDI. The wind speeds that we considered were 110 miles an hour for components that were left over the winter, 85 miles an hour for most components when not under active launch conditions, and 30 miles per hour for active launch stages. The live loads we considered were mainly the crane, but we also had city lifts and personnel and construction materials on the deck. As you can see here, there were 19 different crane positions modeled in our design. This being Alaska, it was necessary to account for snow and ice, especially during the winter months. And the forces were not insignificant. Ice load ended up being about 20% of the dead load, snow about 30% of the dead load, and wind on the ice was about 30% of the wind load. We also considered earthquake loads, however, they did not control over the wind loads. The load combinations that we used are listed here, but I won't go into depth in this slide. We prepared a global model using CSI Bridge and used it for the entirety of the design. The erection of the main truss was modeled as a piece-by-piece staged installation, and the launch was modeled as 12 full launch stages, which were split into 73 substages. In the launch model, the boundary conditions changed from one stage to the next to simulate members moving over supports. And while that gave us the bulk of our design forces, it was necessary to develop local models for specific components, such as roller frames and rockers, where bridge codes aren't really vigorous. The temporary foundations were designed by Geoengineers Incorporated, a slope consultant to KWH, and they were intended to provide vertical and lateral support to the launch bed and to give tie-down locations for the main truss. They used cap beams on vertical and battered micropiles. The launch bed was intended to support 4 main truss panel points during erection and to support 1 moving combined truss panel point during launch, and to allow for load transfer from that panel point to the next panel point. And it provided a launch track throughout that launch for the rollers to roll on. As I mentioned earlier, we used W36 by 529 launch beams, which were basically the largest section available to us at the time, as well as a number of other components. Receiving tower was intended to support the west end of the launch truss and the combined truss at varying elevations. It had to raise the tip of the launch truss about 7 feet for the combined launch, and then lower the truss about 14 feet to its final elevation. It also had to support the strand jacks and their loads for pulling the combined truss across the slide. And the challenge in designing the receiving tower was providing sufficient bracing in the various different elevation configurations without overloading the abutment embeds. Launch truss was intended to extend the main truss for the combined launch. It had to be quickly dismantled at the end of each stage of the combined launch because there's a rock face on the opposite side of the receiving tower. So with every 1 bay of the main truss that was launched, 2 bays of the launch truss had to be dismantled. It was subject to significant load reversals because it went from a cantilever support to a simply supported condition. And the bottom cord also had to resist combined compression and flexure while rolling over the receiving tower. And this is where the 10th edition of the AASHTO was helpful in the analysis. And that bottom cord was a mix of W40 rolled shapes and built up plate girders. And the top cord was W14s, and verticals and diagonals were a mix of various components. The main truss was analyzed throughout the entirety of the erection process. So first we built a piece-by-piece model simulating the actual erection of the truss itself, and then the staged model represented all stages of the launch. And we checked all main truss members and connections at every stage, and there was no allowance for temporary overstress. In some locations, it was necessary to add temporary bracing members, as can be seen here, temporary portal bracing and temporary bracing of the permanent lateral bracing. The east end lowering frame had to be constructed within the launch bed and provide vertical, lateral, and longitudinal support to the main truss throughout the lowering operation. And it had to be, we had to build it in the launch bed while removing the launch bed, so it posed significant challenges in its design and in its construction. But ultimately, it allowed us to lower the bridge about 9 feet in 9-inch cycles. And I'll speak about some of the design challenges that we faced. So the tie downs in between the launch, or the connections between the launch truss and the main truss were certainly challenging. At L0 right here, this tie down was a critical connection. It transferred all of the downward load during the cantilever truss launch, the launch truss launch, and then all the uplift load during the combined launch. There was a need for redundancy without much available space or weight. It used 8 2¼ inch high strength bars connected to beams that were welded to the floor beam via 3-inch thick plates and stabilized using other plates bolted to existing stiffeners. And there were very tight clearances there, so we had to specify the direction of installation for the permanent bolts so that there wouldn't be clashes. At the L3 tie down, this is another critical connection. That had to support the downward force during the launch of the launch truss, which then became uplift force at the end of that launch, and then went back to being downward force during the combined launch. And same as at L0, there's a need for redundancy without taking up much space or weight. We also needed to create an uplift connection between the stringers and the main truss structure because there was none in the permanent design. There's also a need for a longitudinal connection that would not be affected by all those load reversals and would not create a large force couple with the lateral wind load applied to the end of the launch truss. So now Justin's going to talk through a few of the other design challenges that we faced.
Remaining design challenges, one major issue is the interdependence of the main truss and the launch truss. They're integrated together. We completed the main truss design. It was 5% heavier than expected, but we didn't have time to optimize the main truss. It needed to go into fabrication so we could meet our season 2 goals. To optimize the launch, we optimized the launch truss by reducing its weight, maintaining its strength by using 100 KSI splice plates, basically anything that didn't need to be welded, 70 KSI knife plates, cutting out unused steel and knife plates, and trimming the free leg of angle bracing to the extent possible. This is a look at the knife plates and connection plates where we have cutouts. These were made thinner by using higher grade material, and the red pieces are the splice plates that were out of 100 KSI steel. That's what it looked like in the field. This is an example. We had a lot of this double angle bracing. So if you look in the model here, it was a standard shape, 8 by 6 by ½ inch. We trimmed the free angle leg to 4 inch because that's all that was required. The last design challenge we'll speak of is just the temporary support of the main truss in the launch bed in its load path. We're supporting the main truss at the center, not at the ends of the bridge where it's meant to take a load like this. So there's a few things to consider. This is a free body diagram actually of the first issue, which was pre-tensioning the tie-down rods and ensuring that the launch bed structure beneath and the permanent structure were not damaged. And secondly, was the actual load path. This is what a typical location looked like in the field. And if you look at this bottom photo, there is these yellow highlighted load bars. We directly transferred the load through the vertical gusset plates. We did not develop this detail until after the permanent truss was designed. It would have been nice to modify the weld detail on the box members to transfer through there, but this may have been better anyways because it's a direct load path. Those were the design challenges, or some of the design challenges. We went through everything about the project, and now we wanted to show a construction overview by showing a time-lapse photo or time-lapse video. Hopefully it works out, but it looks like things are lagging today.
So while you're getting that started, I would like to welcome Paul Lyles and Don Diggeman, who are going to be moderating the Q&A for today. Paul is the former Georgia State Bridge Engineer, and Don is the current State Bridge Engineer for Georgia. Paul, we can go ahead and start the Q&A with the time lapse running in the background.
Okay, we'll go ahead and ask some questions. There were a couple of questions about the landslide, and you showed how it was progressing over time. They were curious about how did you choose the location of the abutments? The picture shows them pretty close to the slide zone.
So we wanted to maintain the alignment of the road. That we looked at a couple alternatives going above the Alaska Range and going down below as well. But this made the most sense. We actually extended the length and pushed it another 50 feet from when we originally wanted it, because we wanted to stay away from the landslide and some of that susceptibility. So it was really the longest simple span we could go with maintaining that roadway alignment was the main reason.
Okay. Is ongoing monitoring of the slope going on now? Will it continue?
Yes, BGC engineering has inclinometers, LiDAR change detection. We've actually been able to monitor the movement of the soils from where they came from to where they go, and we've been looking at that pretty regularly using Cambio.
Okay. Then we'll go on into design now and ask some questions. See, did the bridge geometry or the truss configuration evolve as constructability constraints arose, or was it pretty much always a Warren truss?
I'll say that since KWH was on board, it was a Warren truss in the solicitation package for the CMGC contract, and it was during the pre-construction phase. I know Jacobs went through a feasibility study of various different types of bridges, but I think it's been a Warren truss since a truss bridge was selected prior to the award of the CMGC contract.
Okay. You discussed the bridge loads when you went over the loads, but then the question was overstress permitted during erection and launching?
Overstress was not permitted during erection and launching, so that's why you saw some of those temporary features, such as the bracing of some of the bottom lateral bracing that was surrounding the bays that were on either side of abutment 1, which saw tremendously high forces when the launch stress was cantilevered out, and that's why you saw that temporary sway bracing, at strategic points that were basically coinciding with where the end of the launch truss was in the main truss and where the stopping points were of the main truss during the launch over the pier.
Okay. How were extreme event stresses handled in the erection phase?
So if by extreme event, they mean seismic events, we considered seismic loading, it ended up not controlling over the wind loads, but it was considered in the design.
Okay. And then you had your wind loads, RWDI.
We also had, wind bracing that was installed over the winter season that, resisted forces up to 110 mile an hour wind, as Chris showed, and we did not need to have that installed during the construction season, but we left it right next to the pier as a belt and suspenders in case unexpected high winds were brought up or forecasted to reinstall.
Okay. What provisions, if any, were made to accommodate future NSTM inspections? And that's the non-redundant steel tension members. We used to call them fracture critical, but anyway.
Yeah, at the time, fracture critical was still being used in AASHTO when we designed this for the LRFD bridge design specifications. We did not try to get out of the biennial every 2-year inspection requirements. I do think there is potential to go back and look at some of the internal and system redundancy to eliminate that, but at the time of design, it wasn't looked at to eliminate that criterion.
Okay. What is the realistic design life of this bridge, or the design life of the bridge, barring any future landslide?
75 years as our code mandates by AASHTO LRFD bridge design specifications, Paul.
Okay. But then we had a few questions on the deck, and one of them was, how is the SPS deck connected to the longitudinal stringers?
With about 9,000 bolts. So they're countersunk. That was an area where we couldn't use the specialized TNA fasteners because they don't make countersunk TNA fasteners. So we had to use standard A490 countersunk bolts. And the deck panels, top plates overlap to amplify the sealing between the panels and protect the intrusion of water into the epoxy resin infill.
Okay. And then how thick is that SPS deck? About
A little over 2 inches.
the whole thing?
Yeah.
Okay. All right. Then I was curious, did you use the steel, at least the bottom plate, did you use that as the section for the stringers, or did you just dead weight?
I'm not sure of that question. So the deck plate is composite. It was designed with composite action.
That's what I was wondering.
And it also is the top flange splice plate.
Okay. So you used them. Okay. What was the benefit of using the infilled deck? The lightweight?
Oh, the reduction in weight
Okay.
for a long span.
Okay.
It was a requirement to maintain the loading capabilities.
Okay. How is the truss camber detailed? Was it dead load, or what did you do for the camber on the truck?
Yeah, it was cambered for the no load fit condition, Paul.
Okay. Question came in that's kind of interesting. Did you take any videos or drone footage? Were your video was that all done with drones?
Well, a lot of it was done with drones. I think everybody can see the slide that's still up on my screen that says questions. This was a drone photo. So drones are restricted inside Denali National Park, but the general contractor Granite was allowed to fly drones for landslide monitoring, and they were also allowed to take progress photos at that time. So yeah, that's the only time that we could have a drone up in the air.
Okay. A couple of questions here was how was the receiving end access for construction of the foundations and temporary equipment? Did you get to the other side when you're under construction?
I can speak a little bit to this. We had an access road that had been maintained by Granite through 2024, and basically at the beginning of, I believe it was the beginning of September of 2024, where we lost the road and access at the end of the 2024 construction season. And then maybe Justin, you can speak to this season's accessibility.
There's mostly just foot access throughout the construction season by walking down a somewhat hairy trail and then up another hairy set of ladders. But in order to bring materials to that side, it was necessary to use a helicopter. That was done on one occasion with it was something like 50 something helicopter loads.
Okay, there was a question about the type of steel used for the main truss bridge. I don't know if you covered that. And then you mentioned the splice plates were 100 KSI.
So the main truss was ASTM A709 grade 50W, most of the steel. The vertical gussets, actually most of the truss gussets were also 70W to help save on weight. So that's what the primary.
Okay. Here's a question. Were you in temperature zone 2 or temperature zone 3 for Charpy V-notch requirements 3? Did you have any problem getting that steel with the requirements?
You know, you don't hear about those issues from the mill because if it fails, they have to remake panels. But,
okay.
you know, I imagine they did have a little bit of problem because the initial steel order was, took longer than it was supposed to.
Okay. Now, I got a couple questions here about what 3D software was used for the integrated design.
Yep, it was modeled in Tekla and brought into Trimble Connect. And then Amazon Workspace was also utilized where Justin and I would be in doing the virtual model approval through those main 3 softwares.
Okay, and then another one was what software was utilized for the local connection members in the finite element presentation?
Yeah, I mean, that was done, well, for the temporary steel, the connection design was mostly done by hand using spreadsheets as opposed to using software. Okay. But for some of the localized models I showed, we used RISA and EDA Statica and CSI Bridge.
Okay. What were the foundation options used by the main truss and the launch pad? You mentioned micropiles. Did you consider anything else?
Yeah, so for the temporary piles, it made sense to look at micropiles because the permanent foundations were all micropiles and that drilling equipment was already present. And it had to be done at the same time in the same season that they were installing the permanent foundations. I can't speak to the options that were looked at for the permanent foundation, but that was why we ended up on micropiles for the temporary works.
Yeah, and for the permanent works, if that's what the question was about, they were modular precast blocks that were post-tensioned in the field together in addition to the micropiles and soil anchors.
Okay, for the top chord and diagonals, did the temporary conditions control the design sizes?
Yes, for several of the main members and their connections, they were controlled by the erection stresses that the structure saw in its infancy, more so than in the final condition, simple supported, that's shown on the screen.
Okay, we still got a bunch of questions coming in. I'm going to turn it over to Don.
Thanks, Paul. We do lots of questions that come in. Was the Tekla model made in final shape or cambered shape?
So I guess both. The truss was modeled in its cambered shape and fabricated in that shape as well. But the stringer system, the floor system, had no camber. It was modeled in its final state, I guess. It conformed to the shape of the permanent structure. There was no need to roll camber into the stringers.
Okay. And this is going back to the the deck connection. This question goes, how do you achieve a reasonable level of friction given the deck is essentially a smooth steel plate?
It's no different than any of the other connections really, in that, it was a steel plate, steel to steel connection. We developed the same friction. There wasn't any special treatment to the deck plate different than any other gusset plates. So,
and for design, we were conservative on the slip coefficient. We really only counted on the deck over the splices of the stringers themselves, and making sure we had what we needed. And so we didn't rely on them a great deal, Don.
Good. Next question. What is the governing load combination for the main truss design? Does it happen during erection?
So I don't have that right in front of me, Don, but I can tell you for many of the members, once again, the connections and their members were governed by erection stresses, and but I don't have all of that right in front of me right now.
Not a problem. Question, how did you get the heavy equipment on the west side before the bridge was launched?
So in season one of the primary goals was to pioneer an access road across. The landslide had not moved that much in the grand scheme of things at that point. So Granite was able to pioneer an access road across. We got a lot of that equipment across in season one, which was the 120-ton telescopic crawler crane that was over there, the front end loader. There was a dozer over there as well that maintained access during the season. And we got the whole receiving tower and all of our specialized equipment, strand jacks and whatnot for the launch across early September of 2024 before we cut off access to the truss, which was a good thing because the landslide greatly accelerated and there was no chance for a road after that. We also used a helicopter in last season to get smaller items.
How cool is that? We got a helicopter on the project.
Yeah.
Yeah, when we have constructability meetings, you usually you can't fly anything in, but in this case, you had to, right? So.
Well, yeah.
Right.
I mean, it was a small helicopter. It was an A-Star, and we could only bring small things. We had to have our stuff together and get things over to the other side before that road disappeared. So oftentimes things were there 2 seasons ahead of time.
Going back to the erection sequence question was there uplift during the erection at any stage?
Yes, there was uplift. I can probably go back. Yeah, so the uplift roller here, this was at the end of the launch truss. So there was more of the launch truss outside of the main truss than in the main truss. So at a certain point during the launch truss itself, uplifting here, and we resisted it with this. And then, as we launched the launch truss out and during construction of the main truss, there was a net uplift force because we were on the tip of the west progressive cantilever, and that's where we had this tie-down system. So we had 3 different bents of tie-down systems. There were six locations, like you see here, total 4 rods at each location coming down from the main truss. So there's 2 micropiles at each location that were directly coupled in to resist uplift. Program testing was a direct pull-out test to ensure that we were achieving those values before we hit it in the real world.
Yeah, if you go back to that previous picture, that's early or the new designers were getting. It's one thing to design it, but to build it's a different story, right? So when you're out there, we're getting close to finishing up here. So last question goes back to the uplift, specifically on the bearings. It looks the bearings for launch truss subject to uplift loads during erection. What is the special design for the bearings to resist uplift while keeping lateral stability and movable?
Yeah, so I think, this picture I have up here, which is, a vertical support, bearing point, which, we have to accommodate uplift. So these are roller cams here, right? We had a wider flange. You can see that this bottom flange goes past the stiffener. So when it transitions to uplift, these cams engage, but sealed bearings, so the structure can still be advanced with the winch. And we have separate lateral guide rollers here and here to allow, to have independence between those 2 systems. You could have tried to incorporate a lateral guide roller into these as well, but it wouldn't have worked very well. We always separate the lateral guide rollers from those. But in the case of the combined truss launch, we had to use, these cam followers as lateral guide rollers. But again, they're a sealed bearing, and this is a frictionless rotation. So that's how, I guess, we resisted the lateral load, but allowed for movement. I think that answers the question.
Well, I think similar to last call, curtain call, I think I handed off to Hey, Kathy.
I also wanted to point out that back in March of 23, we actually had another longitudinal launch webinar. So if you're really excited about longitudinal launches, I really encourage you to go back and watch that one as well. So thank you so much to our presenters. We really appreciate your time. And thank you to Paul and Dawn for helping with the Q&A. And with that, the seminar is complete.